Alrighty, good evening, class. I'm going to be presenting my project for my individual course project for neural networks. And let's get started. So the objective was to develop a neural network architecture that could that uses some training model and takes in data and can either be used for regression or classification. So for my specific purpose, I wanted to create a classification MLP model. So an MLP is a multi-layer perceptron, and I wanted to classify 6 different types of modulation schemes. That's going to be a frequency shift keying, amplitude shift keying, and phase shift keying. To train this model, I'm going to be using an algorithm called error back propagation. And my goal is to first validate the reliability of the classification of the signal. So when you send a certain signal, you want to be able to say within a certain range that can reliably be classified. And then also want to see how usable will it be in real time in a system. So in terms of the goal kind of correlates to what I was just mentioning about using it in a system. So my specific goal and what I've seen others do in terms of when they want to classify modulations, or they want to use the neural network on this thing called an SDR. So here in the camera, I have an SDR attached to an antenna. And the SDR is a software definer. So it's a radio essentially. The radio can be used to transmit and receive different modulation schemes. And the cool thing about an SDR versus traditional radio, to make it quick, is traditional radios have analog circuitry that can usually demodulate and detect signals of limited amount. So maybe you can demodulate and detect AM and FM. But an SDR has not only analog section, but a digital section that is used for demodulating and detecting signals. And a lot of it is done in software and DSPs and FPGAs and whatnot. And so it allows you to detect and demodulate many different types of RF signals that you may not have been previous to in the past using analog circuitry. And so people are interested in using these model that can detect different forms of modulation to change the type of modulation you're detecting on the fly. So if you're sending AM and then suddenly you switch to FM, you want your receiver, which is the SDR, to be able to also switch to its FM circuitry, which in this case would be software. So my approach is I'm going to develop a multi-layer perceptron for multi-class classification. And the structure of my multi-layer perceptron will be an input layer that has 5 nodes for each of the 5 features for a sample. I'm going to have a hidden layer with 8 nodes with corresponding weights for each node. The activation function for the nonlinearity of the MLP will be the ReLU, which essentially is 0 if your input is less than 0, and then X if your input is X, and where X is greater than 0. The output layer is going to have 6 nodes, which are going to be used to classify each of the 6 modulation types. And then finally, for the output function, we're going to use a softmax for the classifier with the cross entropy as the loss function. So the data is going to consist of samples or symbols of digital modulation schemes. They're going to be generated by MATLAB. Originally, I was going to use real modulation schemes, real modulation signals that I generated off my signal generator, but the signals I were getting were they were a little bit corrupted and not so easy to work with as when I did it in MATLAB. So I went ahead and decided to just do MATLAB and generate the signals in there. And then later on down the line in the future, I can take signals that I generated off my signal generator or received off my signal generator from my SDR, and then I can modify them to get the features. The specific modulation forms is going to be amplitude shift keying, where it's 2-ary and 4-ary. So 2-ary means each bit is a symbol, and then 4-ary means two bits are one symbol. So 0, 0 would be a symbol, 0, 1 would be a symbol, so on and so on. And the same thing for frequency shift keying and phase shift keying. So here to the right, I just wanted to show you all, and let me move my let me just move my to the left here so you guys can see it. Here I want to show just I generate these signals. So for the top one, I have amplitude shift keying that's been corrupted with additive white Gaussian noise to simulate a real channel. because you don't want a perfect. You never get a perfect signal. You always have some sort of noise or fading due to the channel conditions. So here I generated an ASK signal where 0 was -1/2 volt to +1 volt, and then a 1 bit or a bit stream in the 1 got a signal that went from -1 volt all the way up to +1 volt. And you can kind of see the overlap here. When it was 0, the signal was -1/2 to half, and then when it's 1, the signal's -1 to 1. And then the same thing for frequency shift keying. You can see here when it goes 1, here it's 4 areas, so you have 0, 0, 0, 1, 1, 0, and 1, 1, which are symbols that generate certain tones. So here, it's very frequent, maybe like 10 hertz, 20 hertz, 30 hertz, and then here maybe 0, 0, so the frequency slows down and it speeds back up. So here's just a deep dive how I did the tones in MATLAB. They were sampled at 1 kilohertz. I had for 2 FSK, I had tones at 1 hertz, 10 hertz, and for 4 area, I had 1 hertz, 10 hertz, 20, 30. For the amplitudes, 0 was 1/2 volt to -1/2, and then 1 was a 1 volt to -1 volt. And then for 4 area, 0, 0 was 1 volt, 1, 0 was 2 volts, 1, 1 was 0, 1 was 2 volts. I'm sorry, 1, 0 was 3 volts, and then a bit input of 1, 1 was 4 volts. And then for phase shift keying, 0 was 0, a signal with 0 phase shift, and then a 1 indicated a cosine or a signal with 90 degrees phase shift. And then for 4 area, I did a 45 degree shift when you're going from one bit place to the next. So the feature extraction. So what are we using for the features? In terms of what we're using for the features here, we have some basic characteristics that we can take from each of the signals. So modulating a signal, you obviously take the amplitude, phase, and frequency. And in that same thought process, we can say, well, I can take certain features from those signals, extract certain features from those signals that will help me to differentiate between something that was phase modulated or frequency modulated or amplitude modulated. Here, we're going to take 5 features. So we're going to take maximum value of the PSD, the normalized center instantaneous amplitude that receives signals, and then we're going to take 2 phase components, so the nonlinear component of instantaneous phase, and then the nonlinear component of the direct instantaneous phase. And then we're going to take an amplitude and another amplitude characteristic or feature, and then a frequency feature. And here's the interpretation of the features. So the maximum received value, which is gamma max here, is basically used to differentiate between signals with no amplitude modulation and those that had a frequency or phase modulation. So here, this will help us differentiate between an ASK signal or a PSK or FSK signal. The standard deviation in terms of the absolute and direct phase have to do with how direct and absolute phases are calculated for a certain signal. And those two really help us to differentiate between PSK4, so 4 area PSK, and then amplitude shift keying and PSK2. And the same thing for the second signal. It helps us differentiate between PSK2 and the ASK2 and ASK4. Finally, the amplitude, which you would expect, would help you differentiate between signals with amplitude modulation, namely ASK4 and ASK2, because their amplitude, their deviation of the absolute value of the amplitude is going to be different for each symbol versus a frequency or phase shift. The amplitude stays constant, so the feature won't change as much. And that'll help you differentiate between ASK4 and ASK2. And then finally, the instantaneous frequency helps you differentiate between FSK2 and FSK4, because FSK4 is going to be changing, FSK2 is going to also be changing, but not quite as rapidly. So once we collected these features together, we organized them in a row vector with the 5 features. And then at the end, we have the classification index. The index is just a number that correlates to a class or modulation scheme. So ASK2 got index 1, ASK4 got 2, and so on down to PSK4, they got index 6. So this is the MLP structure. This is something I generated on Google, the Google, like Visio or Google Groups. Essentially, I just wanted to show, here goes the input layer with the 5 features. These are the connections. So each layer, each input has a node or connection, or as a connection to the node in the next layer. So in the hidden layer, we have 8 nodes and we have five inputs. So we have 40 weights in total, and each connection has a weight correlated to it. And then after you get past the layer, you go from the layer to the output layer, and each output layer, each hidden layer has a connection to an output layer. And there's 8 hidden layers and 6 output layers, so 48 weights in total. And at the end, you're going to do this weight times the input layer. I didn't have any bias terms here. So after that, then you apply the ReLU as the activation function. And then after you apply the ReLU, you do want to multiply all these nodes by the weights. And then at the end, you apply softmax with the cross entropy. So to get the gradients to back propagate, what you needed to first figure out was how did each thing correlate to the thing that went beyond it, so that we can get the total way the error changes based on a given weight. And then that had a process you had to step back and back and back. So for layer 1, for all the weights, we need to figure out, well, how is the cross entropy related to the softmax, and how is the softmax related to the input to the softmax, and how is the input to softmax related to the weights on layer 2? How are the weights on layer 2 related to the ReLU function, and then how are the ReLU function related to the weights in layer 1? And so for here, using partial derivatives, we were able to solve this. This was fairly simple. The softmax, we calculated the Jacobian for that before in class, so that was simple. The inputs based on the layer is basically just the partial derivative of the inputs based on the weights. The previous weights is just whatever the value was, whatever the value attached to on the hidden layer or the layer before that was. And then finally, the dependency of the weights on the ReLU is just a Heaviside step function. So that can be used here. And then finally, once again, this is just dependent on the input that was multiplied by the weights. And the same thing for layer 2 was done. So this is the gradients that were calculated in the MLP to train it. In terms of actually starting the training for it, so 400 samples were collected here, and for each modulation scheme, 400 samples were collected, and then from each of those samples, 200 samples were selected and combined into a matrix with a total of 1,200 samples. With the remaining 200 samples from each set, 100 were taken to be used for validation to ensure that training didn't overfit, and it provided a fairly decent model. So the weights, the initialization of the model, the weights were generated randomly using the random function in NumPy that NumPy offers, and it just generates weights in the standard normal distribution. So you get like a lot of minus 0.5, -2, -1, +1, -2 point, all those numbers. And learning rates were tested experimentally. So I started with 1, and I decreased by 0.1, 0.001, and so on and so on. So these are the results of classification. Mind you, I will note that this was for all 6 signals with the 200 samples used for the training, and then 100 samples for the validation set. And this is also with a signal to noise ratio of 10 dB. So for each epoch, the number of corrected classes, for each epoch, I went through the validation set, and after I ran the training, I went through the validation set, and I said, hey, validate this after epoch 1. And so then I went through and validated it after epoch 1. And so initially the results were pretty bad because the model hadn't really had a chance to update the weights properly. But it got better as it went on, as it progressed. And here, this graph shows. So I went through, and there were 100 tests for each modulation scheme in the validation set. So 600 in total, because 6 times 100 is 600. And then I went through and added up the correct. If it classified the modulation scheme correctly, I increased that number. If it didn't, I did not increase it. And so you'll see here for the total number of classification successes at the beginning, it's like almost on the order of 10%, and it slowly increases to 50% after 10 epochs. Here's the individual testing. So I plotted as all the classes together, but I also have a plot of all the individual ones. That's amplitude shift king. For 100 samples, you see that it increased after 3 epochs. It increased quite a bit, and then it steadies out, continues growing. ASK4, I believe it doesn't really have a good feature that differentiates it from another signal, and it never changed, or it had some sort of vanishing gradient that was not increasing the weight properly. So it never did show any progress at 10 epochs. I'd be interested to see if after maybe 100 or 200 would it increase. FSK2 actually decreased, which was surprising, to none to say the least. I wasn't sure why it did, but more research will go into that as to why that is the case. FSK4 increased almost 90% after 8 epochs. And finally, phase shift king. You'll see an increase here after 6 to 5. Most of the samples increased after modulations increased after. You'll see here we're almost at 50% classification success after 8 epochs for PSK2 and also for PSK4 per 100 samples for the validation set. And this is a tabulated form of the results from the run. So here you'll see ASK2 going to 56%. ASK4 stayed steady, so the weights were not being updated, or they were being updated too slowly potentially for the amount of epochs I ran. FSK2 decreased for some reason. It started off high, but then went low. FSK4 increased, PSK2 increased, and PSK4 increased. So the results weren't as good as I expected. I had seen others that did this sort of, let me just move my camera here. I've seen others that did this sort of training online, and they got pretty decent results up into the 90% for each modulation scheme, but they ran more epochs, and some of them used 8 features. Some of them used different ways to interpret the module or get features from the modulation scheme. Like some of them used image processing by taking in waterfall, I-fall diagrams to detect the modulation schemes. And like I said, some of them used different features than I used. So unfortunately, it wasn't as good as I expected it to, but 50% after the 10 epochs is still pretty decent. The big issues were ASK4 was unable to be classified. And I did figure out one good thing, which is the FSK4. A good classifier for it is the sigma FA, which I believe is the standard deviation of the instantaneous frequency. It seems to be a good choice for classifying FSK4 compared to other modulation schemes. So that's a good feature to use if you specifically are interested in classifying FSK4. So the problems that I encountered while implementing this was, first off, this vanishing gradient. So using the ReLU as an activation function and then putting 0.5 as their transition value for the input was at 0 helped deter some of those vanishing gradients. In terms of overfitting, I didn't run too many epochs, because when I ran too many, then it started to predict only one classification type for my validation set, and it would predict it incorrectly. So I tried to limit it to maybe 10 to 20. I found that was a good range for me, but like I said, more samples and more features may do better in terms of increasing the number of runs you do. And then finally, the weight initialization. I played around with this quite a bit. I found some weight seeds that were pretty useful for this model, and I used those for a little bit, but then I started using random, and I figured out a good learning rate, and so I sticked with those after a while. So looking forward to next steps. In terms of next steps, I like to be able to test different modulation schemes that were not considered, like QAM, quadrature amplitude modulation, or GMSK, which is used on our cell phones, Gaussian minimum shift king, and OFDM as well. These are 3 or 4 different types of modulation that are very commonly used in different systems that we use on a day-to-day basis. In terms beyond that, I like to also see a sample set with differing SNRs. So in other types of research efforts that did what I did, they used signals with different SNRs. They did an SNR with 10 dB, 20 dB, 30 dB. And so that's what you want to test with, because that's what type of signal you would get in real life. When you have SNR requirements, you try to hit a certain, and that's a dB in terms of your SNR. And so sampling multiple different data sets into your model will help get an accurate prediction if you were trying to implement on something like an SDR, where you're going to be seeing different signals that have various levels of SNR. And then finally, like I said, I would try to extract more features. The features I use are the Sigma AA, Sigma DP, Sigma FA, and then Gamma Max. All 5 of those features are good and are a good starting point, but there are additional features that can be extracted from a signal that can help to classify it. And so, yeah, that was mostly my project. My results are on GitHub if anyone's interested in looking at what I did, as well with the MATLAB code and some of the data plots. So I'll now stop the video and allow anyone to ask any questions in the comments or in class.